In lesson 1, we learned how to calculate a lot of different parts of a projectile problem. For example, how to find the range, or how long the projectile is in the air, or how high does the projectile go, or what is the muzzle velocity of the projectile, or what is the angle at which the projectile is fired. In working with these problems, one of the steps is going to involve componentizing the muzzle velocity. Now again, the muzzle velocity is not always called the word muzzle, which would be the front end of a gun or a howitzer or a cannon, but it's just the initial velocity at an initial angle. We always learned that you're going to need to find the x component for anything that has to do with the x-axis, such as the range, and you have to find the y component for anything that has to do with the y direction, such as the height or the time that it's in the air. And based upon what information you're given in the problem, you should be able to find any of the other pieces of information. Sometimes you're given the initial velocity and angle and you have to componentize it. Other times you have to work backwards in order to find what that final velocity and angle is, by indirectly finding the x and the y components of it. So sometimes you have to take the initial vector apart. Let me draw that here. So if we have a problem like this, and we're talking about that vector and that angle theta, sometimes we have to take this apart into its y and to its x component. And sometimes we can find what the y and the x component is, and then therefore resolve those two to find the original vector and the original angle. Now, it's possible to develop or derive an equation that puts all of these steps together. And that's what's going on in this problem here, problem 3.4. Find an equation for the maximum horizontal displacement of a projectile fired from the ground level. And so if we're looking at it, we're talking about a problem that looks like this, and we fire it at a certain angle. This would be the original tangential vector, and then it's going to have a certain theta, and we're trying to find an equation that helps me find the range, the delta x. And so that's pretty common in AP biology, in AP physics, and that is to derive an equation that can solve for a particular value. And so you might remember that in the previous problem from the previous screencast, that in order to find the range, we had to double the time. The reason being that if you drop something from the height, if you know how long it takes to fall, you can find the height, or if you know the height, you can find out how long it takes to fall. But then when you're going to move to the x-axis, you're going to need to double the time. And you also remember that sine theta is what we use, cosine sine theta is what we use when we go to componentize the vector in the y direction. Then when we componentize the vector in the x direction, we're going to need the hypotenuse times the cosine theta. Now, another thing that we should point out is that since the distance, let's say the distance of the range, which is in the x-axis, is going to be my velocity in the x-axis times the time that it is in the air. That's where this equation right here comes from. And the y cosine theta, the initial velocity cosine theta, is v sub x in my blueprint over here. And so when you multiply this times this, if you remember your identity for multiplying cosine theta times 2 sine theta, you get this value right here. Initial velocity squared sine 2 theta divided by g. And so this equation will work when you are given the initial velocity. You don't have to resolve it necessarily. And you take the sine of twice your angle and divide it by g, and you can find the range. That's not an equation I would bother to memorize, nor is an equation that would be given to you on a test or on the AP exam. It could be an equation you'd be asked to derive. Now, next problem. Another two-dimensional problem, but you'll notice that in this particular problem, you have your typical projectile problem right there, and then in a sense, you've got the second part of the problem, which is when you have a projectile that reaches this point, there is your tangential velocity at some angle, and you're going to have to find the y component and the x component of that particular vector. So it's almost like you've got two parts to the problem. The first part is your usual projectile problem, and then at this point, there's the second part of the problem. So the ball is going to be thrown upward. So you're going to have a motion that is in this direction, so we'll call that motion positive. Down here, when you have motion, that's going to be negative. Your acceleration due to gravity, g, is always going to be negative. We need those signs because we have some motion that is in the positive direction and some motion, like the acceleration cause of motion, is in the negative direction. So how long does it take for the ball to hit the ground? And find the ball's speed at impact. And then the third part was to find the horizontal range of the ball, neglecting air friction. So we're going to componentize our vector and find the x component right here and find the y component right there. And from here on out, we either use the x or the y component depending upon the situation. So once we've componentized it, now we can say, okay, how long is it going to be in the air? And you can put both parts of the problem together. And so we can see that there's going to be the amount of time, the distance, I should say, in the y direction to reach the top of its flight. And then you're also going to have the distance due to the fact that it's going to be falling under the influence of gravity. And that negative sign there is because g is negative. You could have also written like this: v sub o in the y direction times time plus 1/2 negative g times squared. That's how where the negative sign came from. And so when you plug your numbers in, you get a total time to hit the bottom at 4.22 seconds. Now, as is typical in physics problems, we're going to take one value and that we've just calculated, and we're going to use it at least one more time, in this case 2 more times, in the problem. So part B, find the ball's speed at impact. How fast is it going to be traveling when it hits the ground? And in order to do that, we've got the fact that it's got a speed in the x direction and the speed in the y direction. So we're going to use the component of the speed in the x direction, which we found up here when we componentized. And we're also going to use this, the fact that it's going to have the speed in the y direction due to gravity. And that's going to be the fact that it's going to be falling with this particular acceleration, negative 9.8, for this length of time, beginning with a 10 meter per second speed in the y direction, which is from there. Notice that this was going up, so this speed is positive. Notice that this part here is falling, so we could say that this whole part here is negative. And so when we solve this equation for v, we find it's 35.9 meters per second. And then finally in part C, find the horizontal range of the ball. So what we're going to want is going to be the component in the x direction, and that component in the x direction actually we already found up here was 17.3, and it's traveling in this x direction for 4.22 seconds, and we get a range along the x-axis of 73.1 meters. Now here's another problem, and again, a lot of times we are ignoring air friction. We are ignoring surface friction for things that might be moving along the ground. We're also recognizing that engines can change their acceleration. Sometimes we call that thrust. And you can also you can make the engines not accelerate you as much. So all of these things would force you to solve that physics problem in multiple steps to take these factors into consideration. And you'll be doing a lab actually where you're going to look at air friction and the fact that at some point you can reach a terminal velocity where the force upward due to the air friction is going to negate the accelerating force downward, and that's later on in the book. So in this particular problem, we have a jet plane traveling 100 meters per second to the right. It's also accelerating at 20 meters per second every second. And then it's got a rocket evidently. It's going to drop this rocket, and when it drops the rocket, at some point they're going to accelerate that rocket, and then hopefully that rocket will be able to take out an enemy target, like a underground uranium processing plant in Iran, for example. So when we look at this problem and the three different parts, the first thing we're going to do is try to find our velocity in the y direction. And so we're going to use this kinematic equation right here, which we haven't used much. You can take a square root of it later when you solve for y, or you can square root the formula, take the square root of the equation first of all, where your velocity in the y direction is going to equal the square root of the original or initial velocity in the y direction squared minus 2g change in y. You can do it either way, of course. And when you plug your numbers in, remembering that we're talking about negative g, negative 9.8, and we're also talking about the direction going down, which is that's 1,000 meters, and therefore we get our velocity in the y direction. Then letter B, find the velocity in the x direction. So in order to find the velocity in the x direction, we're going to use this equation right here. I think there's some nomenclature that might be wrong here. In any case, yeah, this is supposed to be, that's right, this is all supposed to be x up here, I think. And then this looks like the y direction. I'll let you figure that out because I don't want to use up screen time doing that. And so we've got our initial velocity times the acceleration times time. And this would be the acceleration of the rocket if it is the x direction. And so once we have our x and our y, we can put one down into here and one down into here and solve for the velocity, 411 meters per second. And then we can take those two values again from here and the 386 from there and get our angle. I need to look at that again to see what's going on. I'm not going to spend any time talking about Evel Knievel and his attempt to jump over Hell's Canyon, over the Snake River in the most western part of Idaho. As I do this screencast, I am 3 days away from traveling out to central Idaho, where we'll be within a couple hours of Hell's Canyon. But I'll be mountain climbing rather than going down deep into Hell's Canyon, which is, if I remember correctly, even deeper than the Grand Canyon. But the sides of it aren't pretty much vertical. All right, the last part of this chapter is looking at relative velocity. And here we're not talking about how fast can your uncle or aunt or grandparents travel. That would be a teacher joke. Here we're talking about velocity relative to something. For a long time, scientists thought that maybe there was some absolute frame of reference in the universe, and everything moved according to that frame of reference. They called that frame of reference the ether. And so it was thought that if you went into outer space, space was made out of an ether. And if you traveled in one direction, you might be traveling with the ether, and in the other direction against that ether. Now we know, of course, there's no such thing as ether, because there is no absolute or universal frame of reference. Everything's speed is relative compared to some arbitrary frame of reference which you choose. For example, if you're watching the teacher in the classroom, we think of the room itself as being stationary, and the teacher is moving relative to the stationary wall and floor of the room. However, if somebody is out in space looking down as the earth rotates while the teacher is walking in the room, and they could somehow see that through a telescope, you would have to say, well, what is the frame of reference in this case? Because you'd have to take the fact that the earth is spinning on its axis at the same time that the teacher's walking in front of the wall in the room. And then, of course, not only is the earth rotating on its axis, but it's going around the sun. And so there can be lots of frames of reference. And at the end of this section, the textbook will mention, and what if your speeds are starting to approach the speed of light? Then everything that I'm going to be talking about right now has to be modified, and that's where you get into Einstein's special theory of relativity with length contraction, and it also has to do with mass and time. And that's a much later chapter in the book. So for right now, we need to choose a frame of reference. And the way we designate a frame of reference is by using 2 letters of the alphabet. 2 different letters. One letter represents the position of some object, and then the other letter is the reference frame. The reference frame or frame of reference, same terminology. So if I look at this term right here, AE would be the position of object A, in this case a car, relative to object E, which in this case is the earth. And then we come down here, we have the B represents the position of another car, car B, and E is the earth. And then down here we have the position of car A relative to the position of car B, or the observer in car B. And so what you can see here is, in the diagram, is that if this is the earth right here, and this is my frame of reference, this vector represents the vector that shows the position of car A. And you can say it is at some angle theta with a line of whatever magnitude this arrow happens to be according to some scale. In fact, it looks like polar coordinates. The other thing that you could do is you could use Cartesian coordinates instead of polar coordinates and say car A is this position along the y and this position along the x. So whether you use Cartesian coordinates or polar coordinates, you can describe the position of car A. And we can do the same thing with the position of car B. We can use Cartesian coordinates there, named after René Descartes, 16th century philosopher, mathematician, and person who believed in God. And then this would be a different angle, and we would have the magnitude of that vector as well. And then when we take the one vector and subtract the other vector, the two vectors that I've now drawn in red, when we subtract one from the other, the difference in those two vectors is going to be the vector in x, which is going to be the position of car A as determined from an observer in car B. And you can see that when you subtract these vectors, let's say we're going to subtract it in blue. If I take, if I take this vector in blue and I minus this vector, which is in the opposite direction, so minus a negative, that would force me to add these two vectors together to get that one. And then when I subtract the two vectors, the horizontal vectors, this vector here, and then subtract this vector here, I get a little teeny tiny vector right there, and this would represent the y component and the x component of the vector that is still in black in my diagram. And that would show you the velocity, and we'd have to calculate that would show you the position from the perspective of an observer in car B, position of car A. And we could calculate the magnitude of that vector and the angle from that right triangle. So that's a matter of subtracting the two to get the relative position. Now, as I mentioned earlier, Einstein's theory of relativity says things start to look very different when you start to approach the speed limit of the universe, the speed of light, 3 times 10 to the 8th meters per second, or 186,000 miles per second. Then you have to take relativity into consideration, and that's a later chapter. So here's another relative velocity problem. We have a train traveling with a speed of 15 meters per second relative to the Earth. And so if we disregard the curvature of the Earth, the train is going in this direction right here. I'm not going to draw a train very well. So it's traveling at 15 meters per second in that direction. And then you have a passenger standing in the rear of the train. And this is not to scale, but that's a little person standing in the rear of the train. And they're going to throw a baseball with a speed of 15 meters per second off the back end of the train in the opposite direction, 15 meters per second. So that's 15 meters per second, the speed of the train. This is 15 meters per second, the speed of the baseball. And we're going to say, what is the speed of the ball from an observer who's watching? So if you got somebody standing right here and they're watching this go by, and at the moment the back end of the train is in front of the person in red, let's attach his leg, it's not broken, what will the ball appear to do? And the ball will appear to just fall straight down, because these two speeds moving in opposite direction will cancel each other out. So if you have motion in one dimension, like here, and all you have to do is add the two vectors together. You're adding the 15 meter per second vector of the train plus the 15 meter per second vector of the baseball, which will give a negative sign because it's in the opposite direction, and you end up with 0. Now, the next part of this problem is going to be, well, what if the person throws the ball in the same direction as the train? In which case, when you're throwing the ball in the same direction of the train, you're going to be adding those two speeds together down here, 15 plus 15, and you're going to get 30 meters per second. This is 30 meters per second. And so the person watching this will see the ball moving at a speed of 30 meters per second if they were able to measure that, maybe take a picture of it, flash picture, or rapid, not a flash picture, but now with your cell phone you can kind of take a movie of it, and using that movie you would be able to calculate the speed of the ball and see that the speed of the ball includes the speed of the that the pitcher threw it with and the vehicle that the pitcher's standing on threw it with. So that's pretty easy. Now, what about in 2 dimensions instead of 1 dimension? So here we have a picture of a person in a boat, and the boat has a motor. You can see the motor in the back. It could be a person that's rowing the boat, it could be a canoe, doesn't matter. But let's say that they decide to move directly across the river towards the wharf. Here's the objective, the wharf. And they're going to be moving the boat at 10 kilometers per hour relative to the water. So the boat, relative to the water, is moving at 10 kilometers per hour. The water itself is moving perpendicularly downstream at 5 kilometers per hour. So you've got 5 there, you've got 10 there. What's the boat going to do? Well, the boat is certainly not going to move towards the wharf directly. The boat is going to experience both vectors. In fact, we could take that boat and redraw it right there. And there's the motor. And we could say the boat has this vector from the motor, and it's got this vector from the river. And as a result, resolving those 2 vectors, the boat is going to move in that direction. And you could solve this using the Pythagorean theorem, which would be the easiest way to do it because you do have a right angle. Or you could componentize each vector. The vector that represents the velocity of the boat with respect to the river as a result of the motor. Since the boat is heading in the direction directly across, its x component is 0, and all of its velocity is directed in the y direction if we're using y-axis and x-axis. As far as the velocity of the boat relative to the earth, the water is on the earth, and so this could be the velocity of the boat because of the water as opposed to the earth. In any case, it is moving in the x direction exclusively, and right there. And that's right, the velocity of the river relative to the earth. And let me clean this up. And 0 with respect to the y-axis. And so, and then of course, when you find your x component is going to be 5 right here. And your y component is right there. That's going to be 10. And when you resolve those 2 vectors by drawing the diagonal, you get the same answer, of course. And then when you put those 2 vectors together using the Pythagorean theorem or adding up the components, you get 11.2 kilometers per hour. Notice we didn't need to convert this into meters per second, unless, of course, the problem asked us to, and we can use tan theta to get our angle. Now, let's say that the pilot of this boat has wised up and recognized that they really want to go to the wharf. They have to compensate for the river. And so obviously, they are going to set out in this direction. And so in order to do that, we're going to have to look at our vectors again. And this, by the way, over here, this is a separate problem. So we're focusing on problem A. And so when we want to find the velocity of the boat with respect to the river, we've got these 2 components right here. We're going to have to componentize this vector right there. Here's my y component, and there's my x component. Notice that the x component here to compensate for the river is going to be negative. And the y component is going to be positive. And then when we go and add these vectors together, we add the two x's together, and we're going to get a 5. We add our y's together, and there's only one thing to add. And now we can find our angle, which is going to be 30 degrees. And then here's my component, which is going to give me the boat's going to have to set out at 8.66 kilometers per hour. So that is compensating for the velocity of the river so you can end up at your destination on the wharf. And I think that completes this screencast.